All right, let's open a technical investigation. The incident? A global video call glitching into total oblivion. Our mission today is to figure out why real-time video fails at a planetary scale, and to uncover the architectural blueprint that can actually survive contact with reality. So here's our case file for this investigation. We're going to start at the scene of the crime, that glitch in the globe. From there, we'll unmask the real culprits behind the failure. After a quick call to action, we'll crack the code on a solution that actually works, wrap it all up in an intelligence briefing, and then finally close the case in our mission debrief. You know, every investigation has to start with an incident. And for us, it's that painfully familiar moment when a video call just falls apart. It becomes a frozen, frustrating mess. And let's be honest, this isn't just a bug, it's a crime against the user experience. Our very first piece of evidence is a fundamental law we just can't get around. When you're talking global communication, physical distance equals latency. The speed of light traveling through fiber optic cable is the absolute hard limit. It's the #1 enemy of any real-time interaction, and you simply cannot optimize your way around physics. The number that really tells the story here is round-trip time, or RTT. That's the time it takes for a packet of data to get from the sender to the receiver and all the way back again. And the data is crystal clear on this. Once that journey ticks past 300 milliseconds, the user experience completely falls off a cliff. It becomes borderline unusable. And this really gets to the heart of it. The problem isn't just technical, it's human. High latency creates what a lot of engineers call the walkie-talkie effect. You know what I'm talking about? We start talking over each other, the conversation loses its natural flow, and the entire connection just feels broken, even if the video is technically still running. Okay, so let's move on to the forensic analysis. It's time to unmask the two main culprits behind these massive global system failures. One is that law of physics we just talked about, but the other, well, it's a critical and honestly a very misunderstood infrastructure bottleneck. Our first major piece of evidence is this absolute disaster of an architectural anti-pattern. Just picture it, two people in London on a video call, but their company's only relay server is sitting in Virginia. This means their data has to cross the Atlantic Ocean twice for every single packet. That ridiculous path adds an instant 150 to 200 millisecond latency penalty, and just like that, it pushes a perfectly fine call into the totally unacceptable zone. Now, to understand our second culprit, you gotta know about two key protocols in WebRTC. Think of Stun as the lightweight scout. Its job is to go out and quickly find a direct path between two people. But when firewalls or tricky networks get in the way, we're forced to call in Turn, the heavy escort that has to personally relay every single piece of media. And this is where things get really interesting, because a single centralized Turn server creates this massive cascading failure. It's not just about the extra latency for more network hops. The server's CPU gets absolutely hammered trying to process all that media, your bandwidth costs go through the roof, and then the knockout punch. You get hit with enormous data egress fees from your cloud provider because they charge a premium for every single byte of data that leaves their network. So the crucial point is this. Trying to serve a global user base from a single region setup isn't just a bad idea. It is a guaranteed path to failure. It's an architecture that fundamentally disrespects the laws of physics. Okay, before we dive into the solution that cracks this whole case wide open, a quick briefing. We truly believe the best way to solve these kinds of hard engineering problems is to do it together, as a community. We are building a serious engineering community for folks who really want to go deep on topics just like this. So share this explainer and be one of the first 50 subscribers before February 28th, 2026. If you are, you'll get to join an exclusive introduction session with our team. All right, with our community assembling, let's get back to the case. It is time to examine the architectural breakthrough that can solve this global scale problem once and for all. So the most common first step that teams take is to use Geo-DNS. The logic seems simple, right? Just route users to the server that is geographically closest to them. But here's the question. Is closest always the same as best? Does this actually solve the whole problem? And here, this lays out the core limitation perfectly. Geo-DNS is basically a static map. It knows where you are, sure, but it's completely blind to what's actually happening on the network. Is the closest server totally overloaded? Is there a congested network path? Geo-DNS has no idea. Intelligent application layer routing, on the other hand, uses real-time data, latencies, server load, packet loss to find the absolute best server for you in that specific moment. So the ultimate solution isn't a single server or even a bunch of separate servers. It's a global mesh. a concept often called SFU cascading, and you build it in 4 strategic steps. You deploy hubs in key regions, connect them with a high-speed private backbone, distribute all your core services, like Turn, to every single hub, and then you make sure users always connect to their closest local entry point. The payoff for building this is immense. By handling a user's connection at a local hub, you solve that chaotic last-mile problem. Any traffic between regions then travels on a clean, optimized private network, not the congested public internet. Security handshakes are suddenly super fast and local. And maybe most importantly, the entire system becomes resilient. It can intelligently reroute traffic if one part of the mesh ever goes down. Let's consolidate our findings into a final intelligence briefing. If you walk away with anything from this entire investigation, it should be these crucial points. The big takeaway here is that scaling real-time systems is both a geographic problem and an architectural one. You have to distribute your infrastructure to respect the laws of physics, and you have to build an intelligent routing layer to adapt to the reality of the network. You have to solve for both. And that brings us to the end of our mission debrief. So we've seen the evidence, we've unmasked the culprits, and we have laid out the solution. Building for global scale isn't some kind of dark art. It's a matter of deliberate, intelligent architectural design that acknowledges the physical and economic realities of a connected planet. If you found this investigation valuable, help us build out our intelligence network. Share this with a colleague who's fighting the latency battle. And of course, subscribe to Lalit Official for more deep dives. And don't forget the deadline to join as a founding member of our community. We're looking forward to seeing you there. Mission complete. Thanks for watching.